So that motivates nonparametric regression. Here I'm going to show you how you do it in action. So here I've generated some data. This is my data generating process. You can see that I set up this conditional mean function, that's the black line, and I've sampled 1,000 data points. Those are the little black dots from this data generating process. And after getting all those data, I fit a linear regression. So this is what I said, right? Like if you have some complicated function, you fit a linear regression. Here it's basically telling you that the trend line is flat. And if I were to show you the p-values on this, they're going to be very small. It's going to be very confident about that. But of course, that just means that the best linear predictor is flat. That doesn't mean that the actual relationship in the data is flat. Here, clearly, it is not. And here you can see it, right? You can plot it in 2 dimensions in a scatter plot. It's very obvious that this line is a bad fit, and you would not interpret that tiny p-value to mean that there's really no relationship between x and y. And of course, you know that even if you couldn't plot it, you shouldn't necessarily do that. So what can we do here? Well, and by the way, here I'm using a different syntax for fitting a linear regression. Before we were generally doing the LM syntax, which is the base R version. Here, this is from the tidy models package, which we'll be using for this lecture to do nonparametric regression methods. And in tidy models, you do things a little bit differently. We'll talk about this more in a second, but you just set up what is the regression method that you want to be using. So for example, linear regression or logistic regression. And then you pass that into the fit function where you put in what are the predictors and the outcome and what the data are that you're going to use. We'll see why that's nice. So this is linear regression. Now I can just change this one line from linear regression to this other thing called rand_forest, which stands for random forest. We'll talk about what that is later in this lecture. If I change it to rand_forest, suddenly my predictions are awesome, right? There's still, it's a little bit of jitter, but these predictions are way closer to the actual data than the linear regression predictions were. So how do we do this? And why do we want to is going to be the subject of this lecture, and a little bit of how does it work as well. So here, before we move on to that, let me give you another example in 2 dimensions, because here, obviously, you can tell by looking at the data that this is a poor fit and that something more is needed. But what about in cases where you have more than one predictor? It's a lot harder to visualize, put things on a scatter plot. So 2 dimensions, we still can, but so here's the actual conditional mean function that we're trying to estimate. My data generating process is here. This is this function. I've plotted it in 2D. And then the data I'm going to draw by just adding a bit of random noise to this. So these are the data that I get. And even though I can visualize this, we can make these kind of 3D plots. And I could, if you do this in R, you can actually, the code is in the comments in the slides if you want to play with it. You can actually drag this cube like around or change the perspective so you can see it from different angles. But I promise that won't actually help you decide what kinds of nonlinearities you would want to include, right? So here you might look at this and say, I'm going to include, this kind of looks like a sinusoid, right? So I'm going to make a sine of x term in here and add that in there, and then maybe some absolute value because it seems to be cutting in the middle or something. I don't know. My point is that by looking at the data, it can kind of help you choose what interactions or nonlinearities to include. But even in a simple 2-dimensional case, that's really out the window. There's no way any of you could look at this data and say, oh, I need a squared term or I need a whatever. I mean, it's just impossible to tell. And this is a case where there's actually very little noise being added. It's really just kind of the conditional mean function. So the traditional approach of, I think I need a square. I need a square age, and I need to have an interaction between age and socioeconomic status. I mean, come on. Like you're kidding yourself if you think you can actually look at the data and know a priori from your kind of opinion, professional opinion, what the right interactions and relationships to include are. It's just not possible. And indeed, if you fit a linear regression here, obviously this is crap, right? This is the true function. This is the linear regression fit. This is the best you can do. Linear regression fits a plane. Now you may think, well, let's be a little clever. Let's include some splines. And let's actually be even aggressive with these splines and put an interaction between the splines. So there's going to be a lot of coefficients here that are fitting. And you do this, and this is what you get. Still not very good. Here's this random forest, which I already showed you in this 1D example is awesome. 2D example, same thing. What did I have to do here? Nothing. I didn't have to specify any kind of interactions or squares or anything. It just figured it out, okay? And Here's another example. This is not a random forest. This is another nonparametric regression method called a neural network. MLP is how you do this in tidy models. Also awesome. Very good. Much, much better than this, of course, or even this. So the point is that these nonparametric regression methods, they can learn very complicated functions with basically no user input. These methods are also called machine learning, or sometimes just prediction models, supervised learning. All of this is basically what we've been calling regression or nonparametric regression, or if you want to be dirty, you can say AI. The point of this little demo here is to show you that all of this is really just as easy to do as parametric regression, maybe a little bit more complicated, but not much. You don't end up with any coefficients to interpret, so that's maybe one reason people don't like it, but we'll talk more about that later, why that's actually a feature and not a bug. All right, and in R, the way that we're gonna do these is with this tidy models package. It's, I think, the best that is available in R. It is a wrapper for a lot of different other packages. So for example, neural networks, there's many packages for neural networks. There's many packages for random forests in R. They each have slightly different syntax. You gotta learn how to use them. Tidy model says, basically just wraps all that up and says, here's one unified interface so you can call all of these different methods, just changing one line of code, right? From here to here. I just had to change rand forest to MLP and set this like user parameter, which we'll talk about a little bit more later. That's it. It also has all of these. So all the machine learning models are in this parsnip package. These other packages have little helper functions. So for example, Yardstick has functions for evaluation metrics like AUC and RMSE and precision and things like that. So these are all really nice little packages that you can check out and look at all this nice documentation to learn more about. And there's equivalents, like in Python, if you like Python, the go-to place a package called sklearn. And there's alternatives even in R too. So there's a package that a lot of people at Berkeley use called superlearner that's very similar to tidy models, but we'll be doing tidy models in this course. It's the most popular. So here's some methods that you can use in parsnip, which is the package that has all the machine learning wrappers for the machine learning functions. There's a ton. Obviously you're familiar already with linear and logistic regression. Now you've seen MLP at work and you've seen random forest at work, but there's so many others. Now the point of showing you this is not to intimidate you. Of course, there's a lot that you can learn about, but it's to show you that all of this is kind of at your fingertips and you can just try them, right? I didn't need to know anything about a neural network to run this. I didn't need to know anything about a random forest to do this, right? You just have to understand what the task is, which is I'm trying to learn a function. And here's just a method that gives me a function back, okay? And now you know, of course, because of the stuff that we've learned before, how to evaluate that function and tell if it's any good. And how to think about what, for example, if you're using it for causal inference, what are the assumptions that I'm making about the data generating process? And how might that play into whether this function is an accurate approximation of the true conditional mean or not. So that's what you need to think about. You don't really need to care what are the internals of the random forest or the neural network. That's what is the process through which it takes the data and it generates a function. That's kind of auxiliary to the task. But we will talk about that a little bit just so you have a kind of grounding and an idea. All of these methods you can use, and at this point, I would say, machine learning is a commodity. If you don't know how to do any of this stuff, or you don't know how to combine them, or what, ChatGPT can do this stuff for you. Your job is to understand how to use them and interpret them, not necessarily how they work. So you don't have to be intimidated. Like I said, one unified interface. You just put in the syntax is a little bit different, right, than the LM syntax that we were using. The way that you do it in tidy models is you specify what kind of model you would like to use. Here, we're saying mode equals regression because we're going to be predicting for continuous outcome. If you want to do predict a probability, you say mode equals classification. We're not going to talk too much about that, but it's all very easy to learn. So mode equals regression, and then you take that object. So here we can just do this in R. So library tidyverse. If I do linear regression, I just hit enter. You're going to say this is a linear regression model, but it hasn't been fit yet. So there's really nothing in it. So I could also do like rand forest. right? And that's just going to tell me it's a random forest. So I just set that up, and then I call fit. So fit is where the work actually happens to figure out what are the coefficients, for example, or whatever the random forest is doing, which we're going to talk about that in a second. But this part looks the same as when you called LM, more or less. You put in the specification for the model, so what's the outcome and what are the predictors? And then you say, what's the data that I should use to train the model? And this part, notice, does not change for depending on what method you're using. It doesn't matter. That's the same. You're just fitting a linear regression versus a random forest versus this neural network versus this Mars thing. It doesn't matter. Now, the only thing to be aware of is that when you set up the model, a lot of these models have what are called hyperparameters. So for example, MLP, I said hidden units equals 100. And this modifies the behavior of the method in a particular way. So it's very similar to, for example, when we were doing linear regression and we had splines and we were setting the degrees of freedom, DF, or the, what was the other thing called? Like degree or order of the spline. Basically, some parameters, if you set them to higher values, they will give you functions that are more aggressive. They try to fit the data more aggressively. Lower values are kind of smoother functions. And so you kind of need to understand when you're using these methods to some extent, whether higher or lower values is giving you a more flexible fit or a kind of more smooth kind of fit. But even that, really, you don't, because you can just set these up in tidy models to be tunable and then use cross-validation to pick the best thing, like we talked about a little bit last time in tuning regression splines. So even that, you really don't need to understand. You can just let the computer figure out what the best thing is. So that's the interface. So like I said, this is basically a commodity now. You don't really have to understand the details of all of these methods. We'll talk about them a little bit. But for those of you who are curious, I will say this is kind of the order that maybe you should go in. Random forests are great, I think, for public health and epidemiology because they're really hard to break. It's very hard to, quote unquote, overfit with a random forest. And the predictions are generally pretty decent. There's not a lot of tuning parameters or anything you need to muck with. All the defaults, it's always going to be pretty good. You can then go and learn about these methods here, which will kind of make you a better driver, I think. So the random forest is kind of like your Jeep or your like all-terrain vehicle. This is a thing that will never need any maintenance. And if it does break, you can like fix it with a stick and some sand. Now, if you want to become a better driver, you can learn about these methods. They're not necessarily always going to give you better predictions, but they'll give you better intuition for how these things are working under the hood and what's really going on. And then if you have really bespoke problems, like if you have predictors that are a lot of free text or images, then really neural networks and deep learning are your kind of Ferrari. But they're very finicky. You need a team of kind of specialized engineers to be working on these kinds of things sometimes. I mean, not really, but you kind of, it does take a little bit more expertise to use these. So oftentimes not worth the effort. And here's linear and logistic regression. And this slide is deliberately provocative because, well, what I'm trying to say here with this picture is these methods are kind of dumb, right? They're a little bit naive. They're making very silly assumptions. You're fitting very simple functions that don't really reflect the relationships in the data. But that's only one perspective, because in reality, these things are very useful, which is why we spent 4 lectures talking about them. And they're useful for 2 different reasons. One is that the crazy thing is that in public health and medicine and in a lot of fields, like social science fields, these, like, let's say your goal is just prediction, these are often going to be as good at predicting as a random forest through a neural network a lot of the time. People are often surprised by that because these are so dumb. But there's 2 reasons for that too. The first reason is that there's a lot of noise in public health data in the outcomes that are measured. Basically, we don't really have all the predictors that we need in order to predict this stuff, and so the kind of like missing predictors ends up looking like noise, right? And so there's a lot of variability, a lot of noise, which means that even if your function is nonlinear, you can fit if it's just basically like a cloud, right, of data points. Even if there's some kind of nonlinear relationship, you just kind of draw a line through that cloud, and that's about as good as you're going to get. So linear regression often is a pretty good predictor, or at least as good as other stuff. Not good, but not worse. I'll put it like that. The other reason is that in medicine, social sciences, often the predictors themselves are carefully hand engineered. Like, for example, definition of a disease, like let's say somebody has diabetes, that's a predictor. Well, people have actually, that's a made up category, right? There's no such thing really, but people have thought about very carefully what specific underlying measurements of like blood glucose and other biomarkers and disease states and symptoms and all of those categories have been or all of those underlying measurements have been mashed together into one predictor, diabetes. And it's taken years, decades, centuries even, to think very carefully about what particular constellation of underlying symptoms and conditions should be called a particular disease. And so that disease is actually very carefully engineered to capture a lot of the of the variability that is necessary to explain a particular outcome in let's say, a linear way. So those are two reasons why these things are actually sometimes pretty good in the settings that we're using them, and sometimes hard to beat. Now that doesn't mean always, and that doesn't mean that you shouldn't try. You should always try, and oftentimes you'll see that you can beat them pretty easily. But it's just that people are surprised that sometimes these things do win. Now the other reason that these things are useful to know, even aside from the fact that they can actually do well in certain scenarios, is that even if they always sucked, it would still be worthwhile to think about them, to learn about them, because they provide kind of like a nice little sandbox where you can understand these ideas in a very simple setting. So concepts like root mean squared error, model selection, which we talked about in the past couple lectures, all very kind of friendly setting to talk about those things without worrying about the complexities of nonparametric regression and things like that. So still very useful. That's why I say this slide is very provocative. Yes, these things are kind of toys, but toys are useful, right? There's a reason we play. Play is how we learn. And so that's a little bit about why these things are still important. All right, if you want to learn more about these things, I'm going to talk about regression trees and random forests in a minute, but if you want to kind of go out on your own, this is a great book. It has a website. It's not super mathy. I mean, you're going to see a little bit of math, but they really do their best to even avoid like calculus and linear algebra. There's a really nice website. I think there's even like a bunch of lecture videos online. It's like very, very well laid out here, and it'll take you through all of this stuff. There's also courses here at Berkeley, Stat 154, I think, and CS 189 are both courses that cover this material. As far as I know, there may be others. I think those are a little bit more mathematically involved, at least 189 I've heard. But do caveat emptor, do your own research, see what people are saying on Reddit. Let's give it a shot though. So here, let's fit a random forest to predict charges from all the other variables using this insurance data set. So let's download the data. All right, so in tidy models, we say what kind of method do we want to use? It's random forest, and then say this is a regression problem because our outcome is continuous. We don't want to predict probabilities of categories. And now we fit. So the outcome is charges, and we want to use all other variables, that's our little shorthand, to predict charges. And the data that we're going to use is insurance. Done. So you see this outputs a whole bunch of stuff. This is kind of like the equivalent of the regression summary table. Obviously, there's no coefficients here. We'll talk a bit more about that in a minute. There's a lot of stuff you may not recognize. Here's something you do recognize. This is mean squared error. But we can also compute this stuff. You don't know what OOB means. This is stuff that's specific to random forest. We'll discuss it maybe a little bit more later, but it doesn't matter. Let me show you how you predict from here. So let's save this into an object like we did with LM. We'd save that into an object. I'll call it M for model. And now let's predict. The syntax here is very similar to the LM syntax. You say predict the model. For this model, I want the predictions on the data is called insurance. So if I run that, I get all the predictions back. So this is the prediction for the 9th person, the 10th person, so on. Here, this is a little bit different output than what we get for the LM prediction, because for LM, it just gives us back a vector. And here, what we're getting back is a data frame, a tibble, with a single column in it. And this is because this is in the tidy models framework. everything, they try to make everything kind of come out as a data frame and go in as a data frame, so it's all like plays nice. So for example, if I wanted to glue this to the insurance data so that I can compare the charges to the predictions, right, like this, then I'll get these two columns. The reason you'll see oftentimes in tidy models, you'll have these column names that start with a dot. That's so that you can like glue them to your original data frame. And in case you have a column in your original data frame called pred or called, I don't know, RMSE or something like that, it won't overwrite it. Or it won't give you a conflict that has the same name. So you know that like the dot thing is always the output from some tidy models thing. So a little bit of ugliness in the code, but that's what you pay for having a nice package where everything plays nice with everything else. So anyways, here's the predictions. And now we can compute the mean squared error the way that we have been doing before. So square root of mean of charges minus dot pred squared. All right, that's the mean squared error. Of course, we know this is actually the training error because we have not split the data here, right? So this is a very optimistic, if we then went and applied this for new people and tried to predict their charges, this is a very optimistic measure of our performance. What we need to do is we need to look at the mean squared error for data that was not used to train the model, so that the model could not have memorized the outcomes for these people. So it's easy to do. In tidy models, we can use I think it's initial split. And yeah, we're going to use 3/4 of the data. That's fine for training, and 1/4 for testing. I'll just call that split. And now here, I'll use this data I'll use the training portion to fit the model. Okay, so that's fit. And now here, I need to use the testing portion. Boom. So this is the test error. Of course, that's much higher than training error, but this is actually reflective of the error. So we're getting about an error of, for most people, we could expect predictions that are off by about $5,000. Okay, that's the meaning of that. Let's see how much worse or better we would be if we did this with linear regression instead. So watch this. Here's the amazing thing about tidy models. I just had to change that one line of code. And we can see that the error is much worse with linear regression than it is with the random forest. So this is the benefit of nonparametric regression. There are probably some nonlinear trends here that are being captured by the random forest. The linear regression can't really get its arms around. And that's why we're seeing such better prediction with the random forest. And this is test error. So this is actually what we would expect to see in practice if we applied this model on new data. Last thing I want to show you here, another nice thing about tidy models, you don't need to, most of these like kind of metrics that you would want to compute, you don't need to do it manually. So tidy models, for example, has an RMSE function where you just put in the truth and the estimate, and this is what you get out. And so yeah, this is for the linear regression. Let me change it back to random forest. Okay, so you can see how plug and play this is. Just change one line, linear regression, random forest. Here I can just change one line if I wanted root mean squared error. I don't want that anymore. I want MAE, mean average error. So this is like instead of squaring the residuals, you're just averaging the absolute values, the residuals. No problem, right? Just change that one line, and everything is the same. All the inputs are the same. All the outputs are kind of the same. Only thing you need to be aware of here is that these functions output, like everything else in tidy models, a data frame. So there's a little bit more metadata. So here it says this is the loss function that you used. How did you estimate the value of that loss? Basically, this means you just looked at like this is like the plugin. You look at the plugin version. You can just ignore this basically. And then here, what's the value? So estimate. So if you just want to get the number out, estimate today. Oh, I need to do a poll. this. It's a column in a data frame. Oh, right, dot estimate. Okay, so actually probably this does work. Yeah, great. So if you just want the number out, a little bit more verbose, but I think quite readable in terms of the code. So tidy model is really nice. So takeaway from here is that, yeah, random forest is a lot better in this case.